Right. On the screen. Yeah, it's too late, but hopefully I'll be here. Okay, so welcome everyone. We are very, very blessed to have two incredibly gifted speakers and two incredibly knowledgeable people about one of my favorite topics, and they happen to be space. And I'm sure that if you are here, space is obviously something that is exciting for you as well. It's not often that you get access to speakers like Jim and Jim Square. I first met Jim Adams, how many years ago was it?
2013.
2013, so it was quite a few years ago at the National Science Festival, and he was coming every year or so, and eventually we just got connected, and he became addicted to South Africa. And he keeps coming back, he can't stop. And I've got a funny feeling that it's starting to hook onto Jim Green. Just wait. We're going to get you onto Voltar, we're going to get you onto the good stuff, and you're never going to want to leave. And you know, these two wonderful people are incredibly not only knowledgeable but experienced in a fascinating world. And as I said, I could have read a 50-page CD for each one. We're not going to do that. I'm just going to pick at one or two highlights. So I'm going to start with Jim Green, if that's okay. So he's actually called Dr. James Green, but they call him Jim anyway. And Jim has been working, or he did work in NASA for 42 years. That is a long time to work at any organization. And one or two of the highlights is that he worked at Marshall Space Flight Center, Goddard Space Flight Center, and NASA headquarters. And I was very privileged that it's not often that people get a chance to go to NASA headquarters. But when I did go, thanks to Jim Adams over here, we snuck into Jim's office. And let me tell you, I was expecting to have a whole floor. I mean, you were the head of planetary science and chief science the whole year, but I think they could have given you more space. I'm going to speak to the nation here. What I can say is that through my involvement through other organizations like the Human Mars Summit, I know that you were involved in the Human Mars Summit as well. We start to, like planets, we start orbiting around certain things and we do bump into each other along the way. And it was always the hope that we'd be able to get Jim to come to Cape Town and South Africa. And he's not just going to be coming here to give one or two talks, he's going to go and experience Southern, he's going to go and see salt. I don't mean the condiment that you're going to be throwing on your food. He's going to be seeing South Africa's large telescope. And then they're going out to Carnarvon, and then they're going out to Bloemfontein, the outlet of South Africa. They're going to experience so many wonderful parts of South Africa. And obviously, they're going to get the astronomical delights that we have on offer. And they will be doing a lot of speaking engagements and interacting. But I can tell you that when I say he's knowledgeable, he has won the Distinguished Service Medal, and I see that's from NASA. He also won a medal for the New Horizons flyby of the Pluto system, and of course, NASA's highest honor is the Distinguished Service Medal. So he's not a fly-by-night, he knows his stuff, he really is quite impressive. And of course, he's also been involved in the movie The Martian. Do you know that wonderful movie, Trying to Grow Potatoes? They have to consult with an expert, and he knows a lot about potatoes. So that's why they managed to consult with him. And of course, finally, if there was ever an honor bestowed upon a human being, it would be to have an asteroid named after you. And there is an asteroid 25913, sound familiar? Obviously not. They renamed it the James Green in his honor. And if you ever look up in the night sky, slightly around 3 degrees to the west, you will not see it because it is some airport. I have no idea where it is. Until we saw the naming rights, here we go, and we'll stick to that. So we'd like to welcome Jim Green all the way to Cape Town. So let's give him a very good introduction. This is none other than Jim Adams. Jim has also got a long list of things. You worked at NASA for 40 years.
28. The other
I
job.
was 40 years of aerospace experience.
Yeah.
But you did work for how many years?
28.
28 years at NASA. And I think anyone that spends more than 10 years in an organization, that is a stalwart. When you are going for 20 years and 30 years and 40 years, they are part of the furniture. And that also means they are privy to a lot of information that we as mere mortals wouldn't get to hear. So hopefully they'll share some of those insights when they do their presentations. Jim not only served as NASA's Deputy Director of Planetary Science Division, which was under Jim as well, but he was also the Deputy Chief Technologist of NASA. And if I can just say that those craft that were launched from Earth and went out into space to explore other planets and to go and do readings of things in the near galaxy, he was involved with most of it. Is that safe to say?
That's fair.
Fair to say, there we go. So he's got a lot of knowledge of things like Pluto, because of, let's see, which probe went past Pluto? You know what it was? I'll give you a clue. It starts with new and ends in horizons. Any ideas? New Horizons, that was a very good guess. Outstanding. And of course, Juno, were you involved with the one that jumped onto an asteroid?
Oh, yeah.
He was involved in that. There's a lot of these things that are planned well in advance. You can't just say we're going to send it next week to bump into an asteroid. You're going to plan it 10 years in advance. You're obviously involved in the planning of all those things. Well, hopefully we'll get to share about some of these things, because I know that some people are quite concerned about the fact that in the news, they mentioned an asteroid was heading towards Earth. Did you hear about that? And I bet you are interested. How much time have we got? If I hide under the couch, am I safe? We're going to find out all the information. So who's going to go first? No, Adam's going to go first. Let's give him a walk. I mean, speak so confident.
I've been watching certain presidents
so
in the country.
in fact, you and I first met in this auditorium in 2013. It wasn't until 2014 that I went to SciFest Africa. Very first lecture I ever gave in South Africa was in this auditorium in October of 2013. And it was on asteroids.
Wow.
It was entitled Asteroids, Dinosaurs, and Youth.
Now I remember.
And it was because at the time I had been sent by Charlie Bolden from NASA to help negotiate a telescope to go up on the plateau in Sutherland to help hunt for asteroids. And today, what we're going to be talking about is how important that activity was. And we'll talk a little bit about the status of it as well. So, like I said earlier, this is not Small World's Big Discoveries, and I'm not Jim Green, and this is not Part 6 point. But this is me. And I'll just say, I was born in 1957, just before Sputnik. I spent 27 years at NASA, 10 years at General Electric, and along the way I had jobs at Reed, like an engineer. So I was a systems engineer and observatory manager, then project manager. And this is in green, Deputy Director of Planetary Science, because that's the sweet spot in my career. That's, if somebody asked me, what did you do in NASA? I would say I was Deputy Director of Planetary Science. Best job in the whole world. Not only because I got to work for Dr. Jim Green, but also because the science really made a difference to people. And we were there during an era where just about every week there was some new discovery that would end up on the desk of the President of the United States. So it was a fantastic time to do that.
Then, eventually they start telling you what you have to do in your career, and I was, took sort of a forced promotion to Deputy Chief Technology Officer of the agency. I loved that job, but it was mostly political and it was crazy stressful. So in 2016, I decided to take early retirement, and now I get to travel the world and talk to people about stuff I really want to talk. So that's me. That's me and Dr. Bolden's getting ready to launch the Grail spacecraft. Now, would you like to see a rocket take off? No?
Yeah.
Okay. Then let me just do that in the lab. So this is a Delta II getting ready to launch Grail to the moon. 9, 8, 7, 6, 5, 4, 3. These sound fast.
Yeah.
1, 0, and lift off. Delta II with Grail. So most of what that smoke you see is actually steam. About a minute in, we start seeing pieces of the rocket peel away. That's because they've expended their fuel, and we throw the casing away so they don't have to drag it into orbit. Now it's already faster than the speed sound.
About 1 minute mark. 1 minute into the flight, standing by for solid order. Burnout, about 10 seconds from now. Pressure decreasing on solids.
So the solid rocket will burn out and the seal will peel away.
And we have burnout, 75%. And we have separation.
There's 3 that hang on for a little while longer.
Chamber pressure of the airless mode. 1 minute 39 seconds into the flight. The vehicle now only weighs about 1/2 and put it to the
Did you hear that? After just like 99 seconds, it weighs half of what it weighed on the launch pad.
50 seconds.
And the pieces that fall off, you know where they're gonna fall.
Yes.
Now 21.8 miles per mile. 51 miles per mile.
All right, we'll stop that now
93 miles per hour.
because eventually you just can't see it. Okay, this is another rocket launch that Jim and I were involved in. This one was going to the moon. We had a spacecraft called Laddie, and we needed a rocket, so we assembled this solid rocket and put the spacecraft in a part right here. Now, when you launch a spacecraft, everybody has to get it 5 miles away. Why? Because it's dangerous. They could blow up, right? And we don't want anybody to get hurt. So we all got back 5 miles. Well, everybody but this straw. He didn't get the word. The spacecraft Laddie got to the moon and phoned home. We figured out it was okay, but we never heard from the frog again. Okay, but that's not why we're here. We're here today because earlier in this year, late last year, there was an asteroid that made the press that people started to panic a little bit about. It was called 2024 YR4. Now, why is that important to South Africa? Because the telescope that I came here to help negotiate formed part of a system that actually found that asteroid. So, in a way, South Africa is helping to protect the Earth from asteroids by helping us find them as early as possible. So, I know it looks like a little blip, and I'm like, that's not very impressive. And then somebody put together this little GIF of observations of it, we can see as it crawled across the night sky that the scientists, astronomers were able to, yeah, come on in. The astronomers were able to track it. Well, that's not a normal thing in the night sky. And so they call it a transient and they figure out, well, what's this transient that we're seeing? And they determined that it was an asteroid. But then they start watching it a lot. And they say, okay, well, what's next? Where's it going? Well, in the case of asteroid 2024 YR4, they determined that it was on a trajectory that could possibly impact the Earth. But what happens is when you first see it, there's a lot of error in your measurement. You don't really know for sure. So the error on where the asteroid is going could be much bigger than the distance between the Earth and the Moon, for example. So when they first started calculating the error, they published January 27th, it's 1.2% probability of hitting the Earth. And people go, well, that's pretty high. That's one of the highest we see in a while. And everybody said, well, just wait, let's see what happens. So 1.2% is like right around here. And at that point in time, it's on a path that is 200 Earth radii wide. How far is it between here and the Moon? About 60 Earth radii between here and the Moon. So you can imagine that's a really big area. What's happening is the Earth is inside that big area. So that means that there's a 1.2% chance that it will hit the Earth because the Earth is inside that big circle. Well, as they watch it more, the circle gets smaller and smaller. And what does that mean? Well, the Earth doesn't change its size. And so when you get down here to February 18th, it's actually more probable that it's going to hit the Earth. And most of the astronomers say, don't worry, just wait. And, because it seems like a normal guy, like, oh, it's on a trend, it's going, it's, it was 1%, now it's 3%, eventually it might be 10%, 20%. But in fact, what happened is that circle got so small that the Earth was no longer in it. So the error on the trajectory got to be, see, in March, let's see, the percentage is now 0.004. So 0.004 is down about here, probably this data point here. It's on a curve that's approximately 30 Earth radii wide. So they went from something that was 200 Earth radii wide down to 30. And when they know that it's going to pass somewhere in that circle, and the Earth is not in that circle, then the probability is almost zero that it's going to. So, sorry to disappoint you, but the Earth is safe. Now, how big is it? It was 40 to 90 meters. We don't really know exactly how big it is because it didn't come close enough yet for us to take radar measurements. So eventually it'll probably get close enough and we'll fire up a radar and we'll be able to check that. A little bit of history. It was back in 1960 that Eugene Shoemaker first determined that this crater, which was, and in the day was considered oddball because it didn't have a cone in the middle. They thought that most craters were made by volcanoes. And he determined that actually, no, it was the result of an impact. Something that would have happened 20,000 to 50,000 years ago. And the size of it was about 50 meters and roughly 10 megatons of energy. Fortunately, we weren't around for that. But then once his analysis became understood by the scientific community, craters started showing up everywhere on there. Impact craters started showing up everywhere on there. And there's even one, a really big one, just outside of Johannesburg called Flat.
Freedom Fort one? Freedom Fort?
Freedom Fort, I think Freedom Fort was called Swan. But there's also one underneath it there. So you might be thinking of the one underneath it. So, but fairly soon after Eugene Shoemaker did his analysis, we started finding craters everywhere that were due to impacts. Now, you don't see very many on the Earth because the Earth is constantly resurfacing itself. There's continental drift and plates change, and volcanoes erupt, and there's weathering and all sorts of things. But here are some of the more popular craters. And there's one in Namibia, there's Chile, Quebec, here's Swang in South Africa, Mauritania, so this one is about a kilometer in diameter, and then more in Quebec and Australia. When was that? 2008, I think, was the asteroid that came in over Chelyabinsk. Just to give you an idea of the power. It was a morning, people were on their way to work, and this asteroid that we didn't expect came in over the Russian town of Chelyabinsk. It was later determined that it was about 19 meters in diameter. So a quarter of the size of asteroid 2024 YR4. And as it came in, it started to glow as it went through the atmosphere, the friction created light. People ran to the window to take a look at whatever it was that was glowing outside. Then the sonic boom hit. And the sonic boom blew out the glass in the windows. And the people standing behind the windows got hurt. Fortunately, nobody died. But was an extremely powerful event, and it was just a 19-meter asteroid. So that's when President Obama said, gee, we ought to be paying close attention to these sorts of things. And that's what brought me to South Africa back in 2013. We had some close calls. There's DA 14, February 15th, and I forget which one of these, but one of them crossed so close to the Earth that it went between the surface of the Earth and the belts where the geostationary satellites orbit. It was this one, which is, and forgive me, I know it in miles, 22,000 miles. It's probably 30,000 kilometers.
This is also the date of Chelyabinsk.
Oh, that's right. We were looking at this one.
Yeah, I was being interviewed by Good Morning America about this thing and Chelyabinsk.
All right, what he was saying was he was being interviewed about how close this asteroid was coming, and everybody had their telescopes turned to look at this one, and we got surprised hit over Russia by the Chelyabinsk. And then there's another one. This one even had a little move. So one of the things that President Obama said was find them. And so this is a graph that keeps track of the asteroids that have been found. And you can give it a sense of, get an idea of the size of them. The 1 kilometer ones, which is about the size that would just decimate the Earth. The 1 kilometer asteroid would hit the Earth. It would be bad news for everyone. You can see what's happened is the discovery rate has tapered off. We're not finding very many of those anymore. And so we begin to think that maybe we found them all or close to them. Jim will correct me. Right? But we're still finding asteroids that are in the class of 140 meters-ish. And of course, then we think that there's something like what is that, 38,000 in terms of all asteroids. And there's a population that, by using statistics at the discovery rate, they can sort of guess at how many more we have to find before we know we're 100% safe from being hit by an asteroid.
That number is 60,000.
60,000. So we're at 38,000. We're about halfway to having discovered all the asteroids that could damage it. All right. So now my former boss, Jim Green, is going to talk about where all these things come from and should we be worried?
All right, thanks very much, Jim. Okay, so just a little bit more about me. Really why we're here is talking about small worlds. Indeed, as a planetary scientist, retired from the held a number of positions with Gemini connected, went to many of the centers, and I also pushed astronauts around in neutral point systems. A wonderful career, and really enjoyed myself at NASA. But I'm going to start out by talking about how solar systems are put together. It starts with a massive cloud. We have many, many millions, maybe even a billion clouds in our own galaxy. And these clouds of material come from exploding stars. Many stars actually get so big that, and they're cool on the outer edges, they create dust, and then they push the winds from those stars, and that dust goes out into these clouds. So these clouds have all kinds of chemical reactions going on. Nova explodes, creating high energy particles we call cosmic rays, and they hit these clouds, and the chemistry changes again. And so this is a really dynamic area. So if you can imagine a major cloud that's been disturbed by perhaps a nova or supernova nearby, and the waves of material are hitting this cloud, along with high energy particles that are streaming through it, changing the chemistry, things start to condense and start coming together, creating a small body that then attracts more material, and they get bigger and bigger and bigger, and that's where a sun starts. So here's an overview of what happens after the cloud collapses and creates a star. But the cloud and the size of the cloud tells us the number of stars that can come from that. We've been looking at many different parameters, and scientists today believe our cloud contains maybe 2,000 stars, but perhaps as many as 20,000 stars. Now, as these stars are coalescing and coming together, so are the planets, so are the dust material inside this collapsing cloud starts to accumulate, and it gets bigger and bigger and bigger. Now there's a line here, this dotted line is here because there are different types of planets that are created. Those on the left side of the line, towards the sun, are the rocky planets, and those further away are more gaseous and more icy, because there's a lot of water in this cloud too. Now, this is called the snow line. Okay, it's kind of a funny thing, but it's an important thing to remember, because the snow line runs in our solar system right in an area where there's the asteroid belt. And so on one side of the asteroid belt, there's a lot of rocky material. On the other side of the asteroid belt, there's actually comets, and there are rocky material that has a lot more ice in them. And then there's big Jupiter and Saturn, Uranus, and Neptune. Those are all much further away. Now they're much bigger because as they've gone around the sun, there's much more material to accumulate. One of the reasons why they're also bigger. Now, what's really neat about these is that the asteroid belt, which exists between Mars and Jupiter, is a failed planet. it never came together. And the reason why is Jupiter. Now, we sent missions out to this asteroid belt, and we want to go out there. And the very simple reason is when we go out there, we go back in time. We look at the original material that became from an asteroid to protoplanets, to then larger objects that we know as planets today, as they collide and accrete. And the accretion process is a violent one. So two objects come together, collide, huge explosion, but the gravity then pulls the material back together and forms a larger object. That's what was going on in the asteroid belt, except after the impact, when in this accretion process and materials started to come together, it would move near Jupiter, and Jupiter would pull these pieces apart. So they never had an opportunity to create a planet. And it's just debris that's in the process of forming a planet. Now, it never will form a planet because Jupiter is still doing that. And so Jupiter tugs and pulls on these rocky pieces. And sometimes that pull is so great, it throws them out of our solar system. But it also is just enough to push it inward. And when they come inward, and of course they're going to orbit the sun, and when they come inward and they cross our orbit or come near us, we call them near-Earth asteroids. So the asteroid that is 24YR4 is an asteroid that was made in the asteroid belt and pushed by Jupiter into the inner solar system. Now, how we look for these is with telescopes. And we've had a telescope in space. The astrophysicists used it for one purpose, and after they got done with it, Jim and I grabbed it, and we started using that, and it ran out of fuel, but it also made observation of objects in the asteroid belt. But currently, we have no telescopes that are looking for asteroids, but at least ones on the ground. And of course, it includes the Atlas system, the one that's here in South Africa, and we have then in Hawaii and Arizona and all over the place. Now, what have we been finding? Well, we've been finding asteroids, as Jim said. We really started in the late 90s and added more telescopes. And so let me show you. I think oh, it is running. Oh, sorry. Didn't realize it was running. Let me go back. All right. Let's try this. So notice the date on the bottom. Okay, here's what is the little specks of the asteroids we see. There's 2009. Yeah, I know. And then we're going to update that. Here's 2018. Okay. And we're talking the ones that are out in the asteroid belt. Well, that's this yellow stuff. Because we're actually sitting looking at like we're at Jupiter. And then we come in here. So these are all the ones on the interior, the light blue ones, are the ones that came out of the asteroid belt that Jupiter has thrown in. So there is a lot of debris out there, a lot, okay? And the 60,000 that we've been looking for, and as Jim says, statistically we can determine that's about the number we need to find. Most of them are so small they'll burn up in our atmosphere. If they're in the tens of meters, they'll burn up in our atmosphere. But they get into 50 meters, they're going to make it to the ground. They're going to make it to the ground. And of course, we have some that are much bigger. And Jim mentioned that we have, we're looking for all those that are a kilometer and larger to be really, really big planet killers. I mean, the 1 kilometer would do an enormous amount of damage. And there be some species on Earth that would survive. The 1 kilometer ones I'm not too worried about. I'm worried about several others. There's one that's 33 kilometers. Yeah, I mean, there's some really huge ones out there. And part of the reason why we want to look for these is it's not a matter of if, it's only a matter of when that population will hit the Earth. So we as a species, if we're gonna survive, is actually we're gonna have to do planetary defense. We're gonna have to defend this planet against the asteroids. So in 2016, I created within planetary science the organization called the Planetary Defense Coordination Office. And we have a group that does not define, another group that models and figures out all kinds of dynamics and where they are and where they're coming from and how we can mitigate them. And then another group that goes out and executes a mitigation strategy. And I'm going to talk about one of those mitigation strategies, which is hitting an asteroid from moving. Now, as I mentioned, when we go to the outer part of the solar system, we actually fly through the asteroid belt. Now, even though that figure looked like, if the Millennium Falcon is making its way through the asteroid belt, that's what it looks like. Well, it doesn't, because space is huge. There might be several million asteroids out in the asteroid belt, but it really takes we have to take a hard look at the trajectories of our spacecraft, even fly by one. These are the ones we've flown by. Okay. So this is Vesta, it's the second largest asteroid out in the asteroid belt, and we call this a protoplanet, and it's big enough that it's melted on the inside, and it has an iron core. Okay, it is the seed of a planet. So this is the seed of the planet that would have been made if Jupiter let that happen. All right. Now all these other pieces, what we call planetesimals, fall on Vesta and just make it bigger and bigger and bigger, etc. Now the ones that we have visited in return samples are these ones in the circle. They're really big in comparison. So Vesta is 500 kilometers diameter. And the ones that we've actually taken samples from are less than a kilometer. But in this, you can see they're just very small ones. The first set of samples that were brought back was done by a Japanese-led mission called Itokawa, and that's a small portion of these missions. We do a lot of international missions. In planetary, over the 12 years that I was there with Jim also, we launched 13 missions in 12 years, which is really quite the pace of planetary mission. And many of those involved the international community, so we would work with many different groups in JAXA, the Japanese Space Agency was one of them. And this is Itokawa. And Itokawa went down, picked up some material, brought it back and analyzed it, and it started us on the process of doing more and more of that analysis. Now they brought back the top layer, a very thin veneer, and that thin veneer told us how the solar wind, which is the outgassing from the sun, the wind that comes from the sun is in its outer layers, and that wind gets impinged on these, and so it changes the chemistry. It embeds solar wind material, it does all kinds of stuff, and so think how it holds that's going on. We call that space weathering. Okay. Now, if this looks odd to you, it should, because you don't see any craters. There's no craters on it. It is accreting everything that's coming near it. In fact, you could almost see two big round objects that have saddled up together. And what's happened in this area, all this not rubbly looking stuff, but all the smooth looking stuff is asteroidal dust, and it's moving downhill. Now, I say it that way because the center of gravity of these two objects when they're together is different than the center of gravity of them individually. And so that center of gravity is bringing this material down and is creating these lanes as they fill in the gap between the two asteroids that are spinning together. Okay? So these structures are really kind of immense. It's one big boulder. This boulder is huge. It's 540 meters. Okay. you know, and so this is probably, you know, like a huge housing complex. It's not too far from here, the general. All right. Now, another one that the Japanese went to that we were also a part of, Hayabusa 2, this is the second one. This one is a kilometer in size and it's called Ryu. And it's different in shape. You can see the roundness. In fact, it has this belly band. Well, it has a belly band because it's spinning and all the material is moving down into the equator of the object. So that's kind of neat. And it brought back some fabulous samples. It's called a carbonaceous chondrite. And so it's full of carbon. It's full of carbon. It's very black. It's very dark. It's very hard to find. And this is why we don't know the size of many of these asteroids. We only have an idea. Well, if it's so big, the sunlight shines, reflects, and therefore it tells us how big it is. Well, that's true to a point, but if it's already black, it's already a carbonaceous chondrite, it's really hard to then get an idea of the reflected light and then a match to the size. So that's why we don't always know the size of these. Now, here it is, Hayabusa coming down. And on the review and getting a sample. And we did this with the Osiris Rex, which is the next one I'll talk about. Working, yes, there it goes. So it's positioning itself. You can actually see the shadow of the spacecraft. Okay? It's getting ready, and now it's going to execute. Down it comes. It hits the asteroid, the material flies everywhere because there's hardly any gravity on these things, even when they're big. And then that material goes up a tube, and then that tube is sealed off, and the sample is secured. Man, this is big over big hoops. Okay, and now we've got samples and we're bringing it back. Okay.
Isn't that thing traveling like a few thousand kilometers per hour?
They both are. So both the spacecraft is matching the velocity of the asteroid as it goes around the sun. Okay.
Slow motion.
This is near real time. This is imaging. Then they just put the images together. Okay, so here's ours, Osiris Rex and our mission that we put together. And it also has a sampler. So it will come down, samples, and then it puts it in a capsule. And then that capsule lands in the desert in Utah. I should have mentioned the Hayabusa 1, where we went to Itokawa, that capsule landed in Australia. And it will always come down in the United States. But we got to get a long, flat area. And this one also looks like the Ryugu in a way, although it's half the size. This is 500 meters in size. And it really produced some fabulous stuff. This is a shocker, okay? The material that we found in this asteroid are all the nuclear bases for DNA and RNA. All of them. Okay. Now, glycine, which is an amino acid, and there's 120 amino acids, and we use about 26 of them. But it's easy to make, and we find it naturally all over the place. But finding all the nuclear bases is really pretty spectacular. So we think these objects have something to do with seeding the surface of the Earth over time and creating environments where life might have started. So they have something to do with the life process. Because they've got all the right stuff. I mean, if you're going to create life, you gotta have all the right stuff. And these have it. So that's why this one is actually spectacular. And then it has clays and salts. So clays are made in water. So this thing at one time had some liquid water in it for maybe a short period of time inside it. And it's got tons of amino acids, although it doesn't have all of them. But the shocker is that it has all of them. Now, as Jim mentioned, he showed you where all the existing craters are. But this is a little different. This is Mercator projection of the United States, of the world, which also has the size of things that have impacted the atmosphere over a period of time, 1988 to 2018. And as you can see, the 2013 Chile events one has been the biggest one. And as Jim mentioned, it's between 17 and 19. It really shows you that they come down all over the place. And pretty evenly too.
Which in fact, Jim, I think in recent years, there's been two that have come in over Cape Town.
Ah, okay, okay. Now, the key to this is we can determine size and also probability based on the number and then a little bit of the dynamics based on their orbits. When to expect these impacts, okay? So we can see how often, okay, 10 meters, once per decade, 50 meters once in 1,000 years, 140 meters once in 20,000 years, 1 kilometer once in 700,000, and then 10 kilometers invaded over 100 million year period. Now humans were only a couple million years old, okay? And so they experienced a number of these, a number of 140s, for instance. Now, why is that important? Well, 140 meters is a city killer, and it would affect huge areas. So if you can imagine the United States and Washington, D.C., a 140-meter asteroid hitting in that area, it will take out everything inside this ring road called the Beltway, and then affect all kinds of areas around Virginia. It really has enormous impacts. So we started the process of defending our planet. And we were going to do that. There's several ways to do it. When we chose to try and see if it works, was with a mission called DART. We put DART together to be just exactly that, an object that will hit an asteroid and move it and change its trajectory. Now, what's really brilliant about DART, which actually stands for Double Asteroid Redirect Test. So where does this double asteroid concept come from? It actually came from a scientist in France, from the US Space Agency, French Space Agency, who said at a meeting, we can't be hitting an asteroid that's flying around the sun, moving its trajectory because we don't know how much it's going to move, and then we move it in a way that it hits the Earth. And he tried it. Because we don't know how much we're going to do. We don't know much about how this, what's going to happen. We can only model it in the supercomputer. Now I'll tell you how wrong we were. We were really wrong. We're going to have to pick a special asteroid. The asteroid we picked was named Dimorphos, and it is a binary asteroid with a bigger asteroid called Didymos. So that's what makes it a double. So it has Didymos is here. So Delos is the 780 meter, and Dimorphos is the one that's orbiting. We're going to hit the one that's orbiting. Okay. And we did. We hit it at about 7 or 8 kilometers per second. And it changed its orbit, which was about 11 hours and 30 minutes. We changed the orbit by 5 minutes. That would be what the models told us, and we moved it by 39 minutes. We really moved. And so this tells us there's a range of asteroids that we're going to be able to hit and move. Now, this is not the only technique, but this is the technique we now know works. And so, in the next 100 years, we don't see anything that's large enough that we have to worry about. But as we get to the 200 years, a couple that are pretty big, and we may have to do. And so with that, let's have Jim and I come up and answer any questions you may have. Thank you very much.
we ought to say is that dark mission that Jim was talking about, two of the camera systems that were on the dark mission that led to its success were built by Dragonfly Aerospace in Stellenbosch. So again, the role of South Africa in helping to protect the planet is significant.
Well, thank you.
I'm just curious, if you go back in your slides to one of those asteroids, did I see faces in those asteroids?
No.
Are you sure about that?
Were they smiling?
I saw two smiling faces, but obviously we as humans are naturally
Yes.
programmed to see.
Sure.
So you obviously get a lot of people who come up with these conspiracy theories and the flat earthers and they're telling you things that, you know, clearly that asteroid isn't coming or is coming. So how do you dispel all those myths out there to the general public?
In some ways, and you can't in most ways. So you have to recognize many of the people that believe the earth is flat is because it's not in their experience base that makes it round. They've never been an astronaut. They haven't gone to the moon and looked back. You know, they haven't done any of those things. Those people need to do that before you're going to convince them.
Right, you and I spent a career that depended on the fact that most objects in the solar system are round.
Yeah. Now, it turns out, even the Earth is not completely round. It's actually squished a little. It's wider at the equator than it is, pole to pole. And that's because it's spinning in how it was made. Many of the planets are like that. And then on top of that, based on volcanic material, which has higher mass, it has aluminums and irons, and many major high mass atoms, move to the surface and then pour over. It changes the gravitational structure of the body. And so we call those mass concentrations. And on the moon, it's very hard to do things in orbit. You know, you look at the moon, it's beautifully round. It's not gravitational. It's got these huge dark areas, which are Mars, and all volcanic material that's come up, all high mass material, and changes the heck out of orbits. We fly over them and it pulls us down. Right? And so it's very hard to get a stable orbit around the moon because of these mass concentrations all over the place.
And in fact, that's one of the things that the rocket launch that we viewed was off to examine. Braille was two satellites that would chase each other around the moon, like a cat and a dog.
Yeah, right.
And they could tell how far apart they were, and how that was changing within the width of a human blood cell. And as that changed, you do some really fancy mathematics, you can infer what the gravity is down beneath you, and how that's changing as well.
Yeah, think of a mountain that Gemini, Braille, A and B, and the mountain over there. He's going to get pushed ever so slightly because he's closer. And then I'll come along, and then I'll get pushed. And all you have to do is measure the difference between the satellite. Measure the distance, that's it. And that seatbelt back and forth tells you about the gravity structures underneath.
Now, it's common for us to give out stickers to good questions. Usually we try to start with people that are 14 years old and less. Who here is 14 years old or lower? All right. So who has a question? And then Mr. Steve will hand out and ask. Gotta have a good question.
Jim and I actually have a bet.
Yeah, but it isn't like what they think of.
No. So when we think of looking for life beyond Earth, in the solar system, we're really going to be looking for microbial life.
Algae.
Yeah, or bacteria. Yeah. I would love slime. We could find slime. So that's what we're looking for. The importance about that is we want to interrogate it, we want to see its structure, we want to see if it has DNA.
Yeah, I mean, that's right.
We went there slime first, yes, we'll find out. That's what we're looking for, in the sources, but astronomers that are looking for exoplanets are looking for also intelligent life. Okay, and they use radio telescopes to do that, that's one way, they look for coded radio signals, because the Earth has emitted coded radio signals for 40, 50, 60 years, and we'll probably keep doing that for things more. But the bottom line there is maybe there's advanced intelligence societies on planets, and we can see that coded radius.
And in fact, the square kilometer array and Meerkat, it's all up there near Carnarvon, that we're gonna get a chance to see. They've got several telescopes that have been in partnership with SETI, the Search for Extraterrestrial Intelligence, thank you, Institute. Partnering with them to not just look at radio signals of the emissions of natural objects, but to also look for radio signals that might be from intelligent life well beyond.
All right, so let's answer that question. So yes, I believe there's life beyond Earth. Have we found it? No. That's no. That's my opinion.
That's right. Well, I feel like an alien when I come to South Africa.
You want yeah. It's, What's that I lost?
Yeah, you gotta repeat the question.
Yeah, that's right.
Okay.
Yeah, here we go. This is better. Yeah, use Jim's mic. Yeah. I love this. You can select. I know. Go ahead.
You look at the asteroids,
Yes.
but other odd planets, do they still have craters?
The moon has craters all the way down the little bitty impacts. Because it doesn't have an atmosphere to stop them. We don't have the little bitty impacts because our atmosphere burns anything up that is smaller than about 20 or 30 meters. That's why Chelyabinsk exploded and only pieces ended up on the ground. Didn't come all the way down to the ground and make craters.
So, I see.
Yeah. Craters that we see here on Earth, or let's go to the moon. Craters that we see on the moon, which haven't been destroyed over time, gives us a record of ages of the surface. So when you look at the mare, you only see a few craters, because the mare is volcanic material that's come up and filled in the cratered area and reset the clock of how old it is. On icy moons, if it has an under ice crust ocean, that ocean sometimes communicates to the surface and eliminates the craters. Now, when we look at a moon called Callisto, it's jam-packed with craters. It's one of Jupiter's moons, big moons. The next one is Ganymede, doesn't have as many craters. The next one is Europa, and we can't find hardly any craters. The reason why is all those moons were hit with the same stuff, with this, pretty much over the last 4 or 5 billion years, they should all be cratered like crazy. But water has come up from Ganymede and eliminated them. Water has come up from the oceans in Europa and eliminated them. But not in Callisto. Water is.
It's a really good question.
It is. It's very insightful. So counting craters is a lot of what planetary scientists do because they tell us the age of the surface. More craters, the older the surface. Less craters, something changed that surface and eliminated craters. They all should be the old stuff.
I think that just does stick, right?
Oh, yeah.
Come down with it.
Yeah, you bet. Any other questions? That's time.
Okay, but you have to increase stage.
I'm gonna throw one at you. You mentioned that a lot of asteroids are moving around on thinking and growing bigger as they move around.
Correct, correct.
Is the Earth growing?
We get 100 tons of meteoric material every day. Okay, every day. Yeah, but it's mostly little bitty grains.
Yeah.
Okay, so as we go around the sun, we're plowing through dust that has been laid there by comets that, and they come close to the sun, they heat up, and all the little grains of material that it captured when it was born are then flying off, creating dust tails, and then that dust sits there and goes into the same orbit. And then we fly through those orbits. And then that material comes falling on us. And when it does, and particularly with asteroids that go around the sun that have eventually broken up too, we call them shooting stars. So how many have looked at the Leonids or the Geminoids? And we call them that because this material, when we cross that orbit of the object that left that debris, when we look out, that's the constellation far away that maps to the orbit where we cross it. So all those meteor showers are indeed debris left over by comets and debris left over by asteroids that have eventually broken up. An asteroid goes around the sun and it heats it and it starts creating a less forces to keep these things together, because you have a forward pressure and all kinds of things that happen. It breaks up and it ends up being a ring of material around the sun. So when you go through the orbit, anywhere in the orbit, you go through that material. So once you break it up, it ends up going through the orbit. We know the weight of an asteroid. We only can estimate that, and we do that in a whole series of ways based on size. We typically get density, which then can give us, based on its size, an analysis of its mass. Yes. So yes, we do that all the time. Now, there's big error bars on that, but it's not a question of, oh. Yeah, right. So here's how I think about it. So I don't think in kilometers unless it's stuff that's close. I don't think in miles. I think in certain units. An AU is a unit. I try to make the units, try to make the unit that then relates to something I'm interested in at a far distance. I can tell you the kilometers from here to Pluto, but to me, that's just a huge number that doesn't make any sense. But when I say to me, it is 40 astronomical units together, and then get it. All right, and an astronomical unit, one astronomical unit, or AU as we say, is the distance from the Earth to the sun. Now, what Jim wanted and asked me is, well, how far away is the moon? To me, that's another unit. It's 60 Earth radii from here to the moon. Okay, that's a nice unit. All our geo satellites, the satellite that's sitting right up there above us in the geo ring, for which it's at an orbit that goes around our planet in 24 hours, just like we do, so it's always right there, is 6.6 Earth radii away. So I rarely use anything in kilometers that's more than a continent in size, and I shift to a different unit scale, and then that's what makes it real to me, because I then that's used as a comparison.
Let me add to that. So the other thing that I tended to do was to think about how long it takes a radio signal to get from that destination back to Earth. And so, for example, it takes a few seconds for a radio signal to get from the moon to Earth. From Mars, it varies because the orbit of where Mars is in its orbit relative to the Earth, it varies between 7 and 21 minutes. So when the Mars Reconnaissance Orbiter sends us a picture from Mars, it takes between 7 and 21 minutes to get back to Earth. The New Horizons spacecraft, when it would broadcast the signal back to Earth of the pictures of Pluto, it took 19 hours to get back to Earth. And Voyager, I don't even run it. So
Yeah, so it's days.
it's days, yeah, it takes days for a radio signal from Voyager to get back.
I think from here to Pluto is 4.5 hours.
Oh, that's it. It's 4.5 hours from Pluto, but it's, when I looked it up the last time, it was 19 hours from Pluto. And now it might be more than a day.
Oh, yes.
Yeah, so if you start to begin to use these things to help get your brain around the size of the distances, it's really important.
All right, so here's a math class. So you just gave me this coordinate, and that is from here to the sun, 1 AU is 8-minute lifetime.
Right.
And the Voyager 1 is 140 AU away, then it's 140 times 8 minutes, and that's the lifetime.
Yeah. So yeah, you can do the math. Who's going to do the math? Tell me how many that is, what that is in days. So, but the bottom line is, you come up with, well, you asked the question, you come up with these tricks because the distances are just so immense. You know, an example is it takes us 5 years to get to Jupiter, 7 years to Saturn, right? So 9 years to get to Pluto.
Yeah, but we don't travel.
Yeah, we don't travel in a straight line either, that's right. So,
Or the speed of light.
yeah, we don't travel at the speed of light. So, for example, Juno went out to Mars and came swinging back around the Earth and then on out to Jupiter. Same with the steam.
Yeah.
Right, to Saturn. But New Horizons traveled straight to Pluto,
9 years.
flew by Mars along the way, and picked up a little speed. Jupiter as well, that's right. So it was using gravity assist to increase the speed to get out to Pluto. So it took the astronauts 3 days to get from the Earth to the Moon. And New Horizons probe, we put it on as big a rocket as we could get, and it crossed the Moon's orbit in just 9 hours. And that's how we tried to travel as fast as we possibly could, because Alan Stern, who you know well, was concerned that if we didn't get out to Pluto soon enough, then if Pluto had an atmosphere, as it's going in its elliptical orbit around the sun, that atmosphere might get cold and condense and collapse on the surface. Pluto would be able to measure.
Well, we gotta finish the story, and that is, it had an atmosphere.
It did.
Yeah, Pluto is about the size of the United States in diameter, okay? And it has an atmosphere, and it has a glacier of nitrogen that is moving on the surface, eliminating craters. And in the atmosphere, there's all kinds of chemistry that's going on. As the sunlight breaks up the complex organic molecules and they create chains, and when they get really big, they drop to the surface. And then we call that snow. Gets heavy enough, and those molecules we can make in the laboratory, we call them tholins. And they are red. And so red tholins are snowing right now out of the atmosphere in Pluto. And when you look at a picture of Pluto, you see this red band. That's snow that's coming out of the atmosphere. That object just shocked me. Okay, shocked me.
Do you think Pluto should still be classified as a?
Yes, it should still be. It should be a planet. I mean, it's so diverse, fabulous, beautiful, an atmosphere. So the astronomers decided that they didn't want to make it. That's
Many very early made juice states using that place.
Say that again?
Many very only made a juicy steak using no plates.
Oh, yeah.
Yeah, there you go. Still saying.
But, you know, if you had been at one of my other lectures that I've done here, this is like the fifth time I've spoken at the Cape Town Science Center. There's a graph that Jim had put together. We didn't show it tonight. But if you were in school in 1848, how many how many planets would you have had to memorize?
1840.
Now, I know I knows the answer.
How many four?
3 or 4, you think? Well, the answer is 21.
Yes.
So why? Because scientists, when they make observations, I mean, that's their job, is to look at the world, right? And they discover these new things. And when they discover it, they classify this new thing as something that they already know. So up until 1848, the best telescopes they had enabled them to find what they thought were 21 planets. But then
Here, let me give you the names. Ceres, Vesta, Juno,
yeah,
and they're all asteroids.
yeah. So what happened was in 1849, the Royal Astronomical Society met and they're looking at this data and they said, oh, some of these things aren't like the others. And they created a whole new class of small body objects or objects in our solar system that we then call asteroids. And that left us with H.
Yeah, really, it was the discovery of the asteroid.
Until it happened again. And Clyde Ponlock came along in 1930, and he was looking in the night sky and saw this transient. Remember we talked about transients earlier? What was it? Oh, must be a planet. And that's how Pluto got discovered. Until 2006, when the International Astronomical Union, which by the way met here in August last year, and they met and they said, oh, gee, we've found so many things in the outer solar system beyond Pluto that look like Pluto, might be like Pluto, that we need a new classification. And that's when they came up with the classification of Kuiper belt object, or I guess because people emotionally couldn't let go of Pluto, they started calling them dwarf planets. But so the answer really depends on how old you are. Is Pluto a planet? You know, if you grew up in school with me and the same kinds of memory tools, or I actually had a ruler that had Pluto on it, right? 1 foot, right? I have to shave a little bit of that ruler off. We would say, yes, Pluto is a planet. But if you talk to kids in school today, they would say, no, Pluto is not a planet. It's a dwarf planet or a Kuiper belt.
Yeah. They now discovered about close to 3,000 Kuiper belt objects. Some of them almost like not quite. Pluto is still the top dog. But they estimate there's more than 10,000 of those kind of objects. And Kuiper, where the name comes from, is Kuiper in the 50s said that ought to be debris, particularly icy material that would come together that also contains rocky material out in the outer part of the solar system, debris left over from the collapsing cloud. That's not the Oort cloud, it's something else, dynamic wise. We came up with this idea of moving cloud. And we now call that Kuiper.
Can we ask a controversial question?
Oh, yeah, absolutely. I brought the NASA secret files.
Well,
Only open the NASA.
but as you are aware, there are certain changes politically in America.
How close the NASA?
And they recently announced that they are going to closing the office of the chief scientist of NASA.
Yes, which is I know.
How do you feel about that, and how that can impact NASA's science?
I'm glad he's holding the mic.
Yeah, that's my turn. I'm actually not too worried about it.
And that position was created many decades ago, but it also has come and gone. What you may not realize is sometimes the NASA administrator, the person that runs the organization, may or may not need that individual. All right? And so when Jim Bridenstine came in, and I was brought up from planetary to be the NASA chief scientist, he had many different things for me to do that he wasn't going to be able to do, but relied on me doing it because I worked directly for the administrator. So it's really all about what the administrator needs. Now, the acting administrator that's there has a big job on her hands, and that is interaction in Congress and the administration to determine NASA's budget and moving forward, and doesn't need several things. And so her staff is now smaller than the previous administrator. All right, and that's the way it goes. Now, when a new administrator is actually determined by the administration, and which means the president, and then approved by Congress, and that administrator comes in, he may want, or she may want a chief scientist, and then that organization will come back together. That's happened in the past. It's come and gone. And that's also true for the other office in that area.
Like the one that I helped get started, which isn't decades old. Right, so the Office of the Chief Technologist was first established when I got assigned to lead Jim Green and join Basic Tech, working for Charlie Bolden. And I have to admit, emotionally, it was like watching your baby die or something, you know. But to be perfectly honest, Jim's argument is exactly right. The purpose of the chief technologist, chief scientists, there were a couple of others, were there to assist the administrator. Well, we're having a change in administration, and the role of the administrator and how they interact with the rest of NASA and how they depend upon their staff to interact with the public is shifting. And so, maybe it was time for that to happen. Yeah.
Time for one more question.
It's very politically careful.
I know. Yes.
First of all, thank you very much.
Oh, it's our pleasure always.
I have a question. If I don't ask it, I'm gonna
Regret it for the rest of your life. Don't do that. Don't walk out of here with any regret.
NASA, what is your view on Area 1? What is it?
On Area 51.
Yes.
Oh, listen, I silenced this auditorium one time when I said, I know the alien body count at Area 51.
You hear a pin drop.
It's 0. People were really disappointed. But the point is that Area 51 is a place that was used by the US government during the Cold War to develop super secret aerospace technology, mostly airplanes.
Why do you say what?
Why?
Show you now.
All these other places.
It's no longer a secret.
Have you ever heard of Area 52? But that's what people remember was, like, oh, the bodies from Roswell, like we're taking Area 51. The bottom line is there was lots of things going on in the Cold War that even today haven't been declassified. And so some of that would end up at Area 51 because it was so secure, because it was kept secure because we were testing airplanes like the SR-51 Blackbird, that was just an amazing plane. Even today, I'm still sad. Yeah.
So let me just add one thing, because why are we not still using them? So technology's changed, for which it's not like we can go build it with spot Area 51 and test it. If it blows up, it blows up. And the reason why we don't do it that way anymore is we live in supercomputers. We use such an enormous amount of supercomputers that we get to the point we actually can build it and likely go it work. But in Area 51, there's all kinds of, all test vehicles, all kinds of stuff, we're just not making it well enough. And that's why they're flying debris everywhere. But now we do it with supercomputers. But there's got to be areas in the United States that are quite secure where things are being made. Now, I don't know what the question. All right, we do have another.
A lot of people, say that black holes skew everything way, and black holes can move through space. Is there a theoretical possibility that a black hole could skew the planet?
From our solar system, it's remote. But indeed, when you look out, you see all kinds of different galaxy types. We've got regulars, we've got stars all over the place, but they're loosely connected. And then there's things that are flattened out in a pancake and are spiral arms and everything. Those that have spiral arms and big centers have black holes in them, not really immense, because that's what's creating the gravitational, with dark matter, creating the gravitational structures of these things called spiral arms. Those things are indeed consuming many things that are around it because they're around it. And because it's at the center, there's a lot of mass. That's what gravitational material flows into.
All right, so
Now, before you add, I actually have to have the last word.
no, you can have the last word.
I have to know that this is the last word.
I cannot.
No, you don't.
Well, then let me go first. So I used to do a thing when I would come and speak in South Africa, and I'd say, my mom is really proud of me, but she can't come with me. She sadly has passed away. But what I would tell the students all around South Africa is that I'd like to take a picture to send to my mom. So what we're going to do is we're going to take a picture of the audience and we're going to put it on the WhatsApp channel. How many of you know about the WhatsApp channel for the space tour? Have you seen it?
I'm on it.
Okay, you can sign up for it by going to jimadamsworld.com. There's a link all the way down at the bottom, and you can follow us as we go from Cape Town to Sutherland to Carnarvon, Bloemfontein, and then on to Johannesburg. So.
Can we do it over here? We can get everyone.
Yeah.
Okay, but if you just would smile now,
Do one of those.
and if you don't want your picture on the WhatsApp channel, just cover it. Okay.
Okay, so then you want to have the last word and then we get into the photo, or would want the photo and then the last word?
No, but you have to come up.
Okay.
So I know many in the audience has probably interacted with this gentleman over the years, and he's done a fabulous job here and loves the public, loves the outreach, and has brought tremendous science to Cape Town. So in honor of his contribution, I have something to give. It is a challenge. Okay. Now this is a very special challenge. We cut the metal out of the engineering unit, and we always make two. You make the engineering unit for the spacecraft, and make the final spacecraft. We brought all that material together, melted it, and made only a certain number of challenge.
From which mission, Jim?
Curiosity.
Oh,
So the metal that's on Mars, some aspect of this.
that is incredible.
So I would like to give this to you for all the work that you've done. But you have to realize if you take it out of my hand, you accept the challenge.
I do.
Now let me give you the challenge. Now that you accept it. Your challenge is keep doing what you're doing.
Oh, that's gonna be tough.
Yeah, I know you enjoy it. It's so important. Thank you. For inviting me.
Well, thank you very much. Thank you. We all came out on a midweek, which is amazing. We're going to ask you all, please come up to the front so you can get a photograph of all of you together. And if you want to get separate photographs, you can do that too. happy to stay. So come on down. I mean, and thank all of the people watching the live stream.
Oh, yeah. I don't know. Something, some of
Yeah.